Hello there. So far, we have learned about the basics on limits and continuity. Now, there is actually a nice theorem that arises from these two. That is, if f is continuous at the limit of g of x as x approaches a, then the limit of f of g of x as x approaches a is equal to the function value of the limit of g of x as x approaches. So basically, what this tells us is that given continuity of f, we can move the f here outside of the limit. So you'll see how useful this is later on. For the proof, I'll leave this as an exercise, so you may check the link down below in the description, as the proof uses the formal definition of limits and continuity, and we haven't really discussed the definition formally of continuity. So you may check that one out if you're interested. And so now let's move on to some examples. Starting with the first example, we are given the graph of f of x as well as g of x. Our goal is to find the value of the limit of f of g of x as well as the limit of g of f of x, both as x approaches 0. So before we start, you may pause this video for a while to try this one first on your own. Okay, good. So let's start. So starting with this first one, first observe that f out here is continuous everywhere. As you can see out here, there are no gaps or holes. It's all continuous. So this means that we can apply the theorem. So that is, we can move this f outside. So we'll have the function value, or f of limit of g of x as x approaches 0. This means that we can focus first on the limit inside. So solving for this one, observe that in here, so this is the graph of g of x, and x equals 0 is out here. So it's out here, x equals 0. And observe that as g approaches 0, clearly it approaches negative 3. So we'll have here negative 3. Going back to f, so we now have this one. And at negative 3, the value of the function is, so this one, the value of f is 0. So we'll have 0 out here. That is the answer for this first one. Moving on to the next one, take note that g is also continuous everywhere. Clearly, there are no gaps out here. This is continuous everywhere, no cuts, holes, or whatsoever. So we can apply the theorem again. So that is, we can move this g outside. So we'll have g of the limit of f of x as x approaches 0. So we can focus first on the limit inside. So this one is the f of x, and as x approaches 0, so it is this one. Clearly, the f of x goes to this one, this part out here. So this one is, so it can't be seen, but this one is 2. So we'll have here 2. And then let's find the value of g of 2. So going back to g, so this one, so at x equals 2, this one, the value of the function is 1. So this one out here is equal to 1. These two out here are the answers for this first example. So I hope you got that one. And let's now move on to the second example. In here, we have the limit as x approaches 1 of the absolute value of x minus 1 over x squared minus 1. Again, you may pause the video so that you may try this first on your own. Okay, good. So let's try this one out. Observe that if we solve this one, we first need to take note of what the value of this one. And we know that in absolute value functions, this one is equal to negative x or x if x is less than 0 and if x is greater than or equal to 0. Unfortunately, it's quite problematic out here since we have a fraction. So it's not really that easy to answer this immediately. But take note that we can use the theorem that is presented in this video. So that is, what we can do is we can let f of x be equal to absolute value of x and g of x to be equal to x minus 1 over x squared minus 1. Observe that given these two, f of g of x is equal to this one. Now moreover, take note that absolute value of x out here, the f of x, is continuous everywhere. So we know that one from the previous video, that absolute value functions are continuous everywhere since their function looks something like this. So it's just continuous everywhere. So this means that we can apply the theorem. So that is, given the limit in this problem, we can move the absolute value function out here, outside the limit. So we can focus first on the limit inside, and observe that if we plug in 1 in this function, we'll obtain 0 over 0, which we know to be an indeterminate in limits. This means that we still need to apply certain techniques in solving for this limit. Fortunately, we can use the factoring method. Indeed, observe that this denominator out here, x squared minus 1, is of difference of 2 squares form. So just to take note, difference of 2 squares is given by a squared minus b squared. And we know that to factor out into a plus b times a minus b. So applying this one to this x squared minus 1, we'll have x minus 1 times x plus 1 in the denominator. And then we can divide the x minus 1s. We can do that since we know that we're dealing with values approaching 1 but not exactly at 1. So this one is not 0 over 0, so we can divide that one. And so we'll be left with 1 over x plus 1. Plugging in 1 to this function, we'll have 1 over 1 plus 1, or when simplified, this is 1 half. And so the value for this is equal to 1 half. So take note that it is immediately 1 half since absolute value of 1 half is just simply 1 half. And so this out here is the answer for this problem. So I hope you got that one correctly. And let's now move on to the last example. In here, we have the limit of the greatest integer function of 2x squared as x approaches 1 half. Again, feel free to pause the video so you can try this one first on your own. Okay, good. So let's start. In here, we can first start with taking note that in here, similar to example 2, we'll have some problems since we know that in greatest integer function, so given this one is equal to 0, 1, negative 1, depending on certain values of the form like this one. Such. So it's not really quite easy, especially this one since we have 2x squared out here. But fortunately, we can immediately answer this one using the theorem. So using the theorem really simplifies the solution process. So what we can do is we first let, similar to example 2, we can let f of x be equal to the greatest integer function of x and g of x to be 2x squared, so that this one is equal to f of g of x. And so in here, take note that the limit as x approaches 1 half of 2x squared, so to obtain this, what we do is we just plug in 1 half out here since 2x squared is just a polynomial. So plugging it, this one out here, will have 2 times 1 half squared, or is equal to 2 times 1/4. Then 2 divided by 4 here, we'll have 2 in the denominator, and so we'll be left with 1 half. Given this, take note further that the greatest integer function of x is continuous on x equals 1 half, continuous on this one, on this limit. And why is that? Well, we know that from the previous video, greatest integer functions are continuous when the value of x is in between integers. Indeed, 1 half is in between the integer 0 and 1. So we know that in this part, it is continuous since in the graph, it looks something like this. Oops. So even though there are some gaps when this one is in between two integers, so this one is an integer. Oops. Let's just put 0 here and 1, and 1/2 is out here. You can see that the graph is continuous out here. So this is indeed true. And so given that, we can apply the theorem that we have. That is, given the limit in the problem, we can move the greatest integer function out here. So we can focus first on the limit inside, but fortunately, we already obtained that from above, out here. So that means we know that the value of this limit is equal to 1/2. Going back to the greatest integer function, we know that the greatest integer function of 1/2 or 0.5, so the greatest integer present in this one is only 0. So this out here is the answer for this problem. So I hope you got that one correctly. And yeah, this is the last example for this one. I hope that you see how beautiful this theorem is in dealing with the limits of composite functions, since it really makes the solving process much quicker, more efficient, faster, and simpler in total. So yeah, that's it. I hope you enjoyed and learned a lot from this one. Feel free to comment down below if you have any suggestions, recommendations, or whatsoever for this video, this playlist, and this channel in general. So yeah, that's it, and that's all for this video.